Everything isn't important at this stage of the game. So just stating that something is circle B actually has a meaning. That indicates that B is the center. You can't just go by looks. Just because it looks like it's the center doesn't mean it is the center. So the name actually tells you something. You might see something like this. A circle with a dot in it and then a B next to it or a letter next to it. That also indicates that that letter is the center. If that's the center, let's label it. That's the diameter. Let's label this as a radius. There's more radii in there. I'm just going to label one of them. If you now know that you have radii, you should be able to put slash marks to show that that's equal. That should be something that goes through your mind immediately. What are we going to call this thing? All right, let's label that. Chord. What about this thing that is touching once? Tangents. That might appear as a segment, it might appear as a ray, it might appear as a line, but it's intersecting once. You got to start with something. So they're giving us these things. What are these things? What are they, though? Are they segments? Are they arcs? These are arcs. So we're not placing these degree measures inside of an angle. We're placing them on the outside of the circle. This arc from D to C is 80 degrees of the circle. This arc from D to E is 68 degrees of the circle. What's the whole circle? 360. What's half the circle? 180. So if this is the diameter, and that's 80, what would F to C be? Wouldn't that be 100? If half the circle is 180 and you already know the 80, don't go by looks. It looks like they're equal. You go by numbers. If that's 80, then this one's 100. If this is 68, then what is from F to E? 112. Put that in. You might need it, you might not. We don't know. But that's what should be going through your mind as soon as you see a circle diagram. Look for the diameter. Do you have it? Do you have any radii? If you do, put some slash marks in there. Do you have some chords? Do you have tangents? What is it that is in front of you? If you've got partial pieces of your arcs and your circle and your circumference, then try and figure out what the other ones are. If you've got diameters and things that will cut the circle in half. Last time, did we discuss central angles? Did I discuss the big three? Yes, they're on the sideboard. They're written in green right here. We said that the central angle is always equal to its arc. We said the inscribed is half of its arc. We said that the tangent chord angle is half of its arc. Well, DBE is from here to here to here. Its center, its vertex is the center, so that makes it a central angle. That makes this 68 degrees. That's our rule. You could call that a definition, a postulate. It's obvious because it's not as if they're two separate things. We're taking the 360 degrees that are in the center and we're just expanding it out to the edges of the circle. That's all we're doing. We're taking all these angles that are in here, expanding them out. I think last class we talked about intercepting arcs. Did we talk about that? This angle intercepts this arc. It catches it. So 68 degrees, our rule here is that it's equal to the arc that's caught. Next angle, FDC, that goes from here to here to here. That's not emanating from the center. That's got a vertex point that's on the circle. What arc is that angle catching? From here to here, right? Well, what's the rule for an inscribed angle? Half of the arc that it catches or intercepts. What's half of 100? 50. That's going right here. We're going to prove that the day after the SOLs. We don't have time now to show why that actually is true. We'll do that when we're done with the state testing, which is either going to be May 8th or May 12th. We've been given some specific days now. So your test will either be the very first Friday of May or the Tuesday that follows. We've also got an angle up here formed by a tangent and this chord. What is that catching? What has trapped in between? 80. What's the rule for tangent chord? Also half of its arc. So this angle right here, 40 degrees. We don't have a special name for that, it's just tangent chord. And the rule is the same as an inscribed. Half of the arc that is being trapped or caught or intercepted by the tangent and the chord. Those are the big three. You got angles coming from the center, angles that come from the circle itself, and then an angle that's kind of inside and outside. Major arcs we want to be more than 180. So I just put down as many letters as is needed to be more than 180, either clockwise or counterclockwise. Let's see, looks like F to C to D to E will take care of that. And I just give a big arc symbol above it. Just make sure that you are going on the perimeter of the circle, the circumference of the circle, in one direction or another, clockwise or counterclockwise. And if you see a half circle, usually it'll be referred to as a semicircle. Page 2. Once again, the name of the circle is actually telling us something. That's telling us that D is the center. That's telling me that this is a radius. This is a radius. It tells me that those two are equal. Start looking at what else we have and labeling it or thinking about it. This thing is touching at one point. Let's label it as a tangent. All of these are touching at one point. This one touches at R. This segment from W to P is touching at M. So I've got three tangents that are surrounding this circle. You could say that the circle is inscribed, or that the segments circumscribe the circle. And that leads to the first rule on this page. Previous page had three major rules: central angle, inscribed angle, tangent chord. This one's going to have two rules. First one is that radius and tangent are that symbol? What's that symbol? Perpendicular, which means how many degrees? Put that into the drawing. If I see a radius and a tangent, right angle. Radius and tangent, right angle. That's on the sideboard. That's written in blue. Anything that's not red means that it's got to be memorized. You got to start with something. So we've got some given information here. That says 30 meters. If that radius is 30 meters, isn't this one 30 meters? People are putting their slash marks in the drawing and then forgetting what it means. It means that they're congruent. It means that they're equal. 72 is from here to here. 72 meters. I've got a lot of people who are confusing distances with angles. Do you see any degrees on the 72 or the 30? No, so it's not adding up to 180, it's not adding up to 360. The only thing that's an angle in here is our right angle. Jacob. Yes, I'm not labeling that because I don't have a point that's important to me right now. 30, 72, let's now take a look at what we're actually trying to find. We're trying to find DV, which is from here to here. What do you think's going on here? What kind of triangles are showing up? Right triangle. How am I going to find that? How about C squared, A squared, B squared? Got to bring in your right triangle work now. I've got 30. That's this side right here. I've got 72 here, so I'm really just doing Pythagorean theorem on that. Can you do that right now? Tell me what that hypotenuse from D to V turns out to be. I'm done going through the work that's needed for Pythagorean theorem. You guys should know what that is. Did you say 78? All right. He's getting 78. Just check and see if that matches up with your work. And put it in the drawing. When we were proving that triangles were congruent, we had SSS, SAS, ASA, AAS, and what was our fifth?
HL.
HL. Do I have right triangles? Do I have a hypotenuse that's the same for both triangles? Do I have a leg that's 30 and another leg that's 30? I've got right triangles where the hypotenuse is the same and two legs are the same. I've got HL. What does that tell me about these two triangles? They're congruent. So what is R to V? Put a 72 in there. That leads to our next rule. Down here we'll put another rule. The way I describe it, if I'm out here at V and I want to get back to the circle and I can only travel on tangents, I could either go this way to T or I could go this way to R. Either way that I go, it's going to be the same distance. So if I'm living here at point P and I want to come back to the circle, I got two choices. I can go to R, I can go to M. Either way, that's going to be the same distance. The same with W. If I'm up here at W, traveling back to the circle will always be the same length. I call those tangent distances. angle. That's my terminology. I call it tangent distance when I'm outside the circle and come back to a tangent point. Do you have some given information halfway down your page? Does it say PR and TW? Does it have meters next to it? That should be meters and meters. Is that on your paper? No, put that in. Those are meters. And put them in the drawing. You've got 32 meters right here. You've got 14 for TW. That's up here. But I just said, according to this rule, that this should also be 32. And this should also be 14. Mistakes that my other class is making. They're thinking that from here all the way to the other exterior point is the same as maybe from here to here. It's not from external point to external point, it's from external point to a tangent point. Can you now find the perimeter of the big triangle WPV? How do you find perimeters? Add it all up. My other class was adding in 30, 30, and 78, so I want to add that in. No, I'm only interested in the outside perimeter pieces. What does all that add up to? 236. 236. And we're still talking meters. A lot going on here, but it's really only two rules. We saw a radius and a tangent, we put in a right angle. That allowed us to do Pythagorean theorem. Then, because we had congruent triangles, we figured out that tangent distances are equal. That allowed me to duplicate the 32s and the 14s and the 72s. And then I could find more information from that. Is there anything else on this page? I threw this in because people aren't naming things correctly. They're throwing down distances when all I want is a name. The radii are dt and dr. Don't tell me it's 30. I don't want to know that it's 30. If you name something, put the symbol above it. You want a segment symbol for those two segments. Last page. Another circle, another name. That tells me that this is the center. That tells me I got radii here. I've got some given information. It's not degrees, it's distances again. So 30 and 36. From here to here is 30. From here to here is 36. Is it pretty obvious that this is not drawn to scale? What do we call AB? That's chord. What do you call CD? The radius. What is the radius doing to the chord if you're seeing this in your drawing? Bisecting. That's our rule. And that's what I've got on the side board on the very bottom. Radius bisects chord. Double arrow. Radius and chord are perpendicular. So what I'm showing you is one direction of this arrow. I'm showing you what happens if you see a radius bisecting a chord. When you see a radius bisecting a chord, you're allowed to say that it's perpendicular, so what can I put into the diagram? 90 degrees, put some right angles right in the center there. That's one direction. It turns out I can work this the other direction also. Hence the two arrows. So if I see the right angles with a radius and a chord, what can I then put into the drawing? Slash marks. So if you see the right angles, put the slash marks in. If you see the slash marks, put the right angles in. What happened the last time we put right angles into the drawing? Do we use Pythagorean theorem? I'm looking for CB. CB is the hypotenuse of this right triangle. It would be good if I knew from B to E. What are these two parts here? How much? 15. We got 30 here for a reason, so that we can break this up into 15 and 15. So I'm doing Pythagorean theorem on that blue rectangle, triangle. I meant triangle. C squared, I've got 15 squared for a leg, 36 squared here for the other leg. $39. Even though there's a lot going on in these drawings, you got to think about whether you're looking at chords, radii, tangents. It boils down to the rules that I wrote on the side for. First page of this circle basics were basically those three. Next page, radius and tangent are perpendicular and our tangent distances are equal. And then the last one is an if and only if statement. If you see a bisected chord bisected by a radius, you can put in the right angles. If you see the right angles with a radius and a chord, you can put in the slash marks to indicate that it was bisected. What's next on our agenda on the front?